It turns out that there are two main ways to define sequences, and we've only looked at one of them so far. So the way that we've already seen is to say something like a sub n is equal to 2 to the n plus 1. So this would allow us to plug in n equals 100, for example, and figure out right away what the 100th term is in our sequence. And that would be called an explicit expression for our sequence. But there's another way that we could talk about sequences, and that's through a recursive definition. And a recursive definition relates the terms in a sequence to each other. So for example, we could look at this recursive definition where we're saying that b sub n is equal to 2b sub n minus 1 plus 1 over b sub n minus 1. And the point is that this is relating the nth term in my sequence to the previous term. And so we could use this to figure out what the next term in my sequence is based on the previous one. And so in order to have a complete recursive definition, we're always going to need what's called an initial condition, which just tells you how the sequence starts. So let's look at a couple terms in the sequence just to make sure that we understand how the sequence is built. So we already know that b sub 1 is equal to 1. And then if I plug into the starred equation, I can figure out that b sub 2, just plugging in n equals 2, is going to be equal to 2 b sub 1 plus 1 over b sub 1. And so now I can just plug in that b sub 1 is equal to 1 to figure out that this is going to be 2 plus 1, or in other words, 3. Now I could use this information to figure out what b sub 3 is, because I know that b sub 3 will have to be 2 b sub 2 plus 1 over b sub 2. And then I can plug in the computation I just did on the previous line. And so that should be equal to 6 plus 1 over 3. And if I feel like simplifying this, you could see that this is going to be 19/3. And at this point, hopefully you can see that I could do this procedure indefinitely, because I know that b sub 4 is going to be 2 times b sub 3 plus 1 over b sub 3, and then I could plug in what that value is and keep on going forever. And so this recursive definition really would allow me to compute what b sub 100 is if I felt like it. And so it turns out that there are situations where it's really easy to find an explicit expression for a sequence, but sometimes that's not so easy, and it's much easier to find a recursive expression for a sequence, or sometimes it's easy to find both, or it's hard to find both. But in any case, sometimes a recursive definition can tell us more about a sequence than the explicit definition can, or vice versa. And so we want to be used to using both types of definitions. And so because we're talking about calculus and we've already talked about limits of sequences, we're going to want to know how to find the limit of a recursively defined sequence. And so it turns out that often what we're going to need to do is to assume that the limit actually exists. So let me rewrite that. So we're going to assume that the limit as n goes to infinity of b sub n exists and is equal to L. And so this is actually quite a strong assumption, and we might have to do some work to actually show that the limit exists. But for now, we're not going to worry about that, and we might find some tools later on that'll help us show that a limit actually does exist for a sequence like this. But if we do know that information, then we can write that the limit as n goes to infinity of b sub n, we know that this is going to have to be the limit as n goes to infinity of 2 b sub n minus 1 plus 1 over b sub n minus 1. And so the reason that we know this is because I'm just plugging in the recursive definition for b sub n. And so I haven't really changed anything. I'm just carrying the limit along for the ride so far. And now I'm going to want to use this information right here that I just assumed that this limit was equal to L. And so on the left side of the equation, that just becomes an L right away because that's the same expression. And then on the right side of the equation, the fact that each one of these terms has an n minus 1 in it doesn't make any difference when we take the limit as n goes to infinity. And so for that reason, the right-hand side is just going to be 2 times L plus 1 over L. And so that means at this point that we've shown that if the limit exists, then the limit L will have to be equal to 2 times itself plus 1 over L. And at this point, we can rewrite this. And so if I sort of move this L over to the other side, then I'm going to get L plus 1 over L is equal to 0. Or in other words, L is equal to negative 1 over L. Or in other words, L squared is equal to negative 1. Or in other words, L would have to be equal to plus or minus I. So in this case, the only way that the sequence can have a limit is if it is an imaginary limit. And we can actually tell that for this problem that's not going to be possible because the sequence had only real numbers to begin with. And so this example shows that in this case there's actually no way that the limit could exist.